Here we want to look at an example of a particle traveling along a curved path. Here, a circular path of a radius of 2 meters, and using actually the NT, normal tangential coordinate system or components, to find the magnitude of acceleration. So a particle starts from rest at the top of this circle and travels a distance of 2 meters along the circle with a constant v dot of 4 meters per second squared. In fact, since the definition of A sub t is dv dt, and that's v dot, so basically we have our tangential component of acceleration. By the way, the objective here is to find the magnitude of acceleration at that instant when the particle has traveled 2 meters. So we already have the tangential component of acceleration. We know whenever an object travels along a curved path, it does have a centripetal acceleration or normal acceleration. So how do we find this normal acceleration? If we have v dot and we have the distance traveled, and v dot, remember, is tangential, rate of change of speed, how could we find normal acceleration? Now, normal acceleration is velocity squared divided by rho. Now, rho we already know is 2 meters. That's the radius of curvature. But the question is, how do we find velocity at that instant? Well, we know that one other way to define acceleration instead of dv dt is as v dv ds. So bring in the position. And if we do a cross multiplication of this, v dv becomes a ds. So here, of course, a is a sub t. And if we go ahead and integrate this, so v dv, and put actually the limits, and remember, a sub t is a constant 4. So if we go from, let's say, when position is 0, velocity is 0, remember it starts at rest. Then the position is 2, what is velocity? And that's exactly what we want. We want the velocity. So we get 1/2 v squared evaluated between 0 and v. And the integral over 4 with respect to position becomes 4s evaluated from 0 to 2. So if you plug in, we get an 8 on the right hand side and 2, if you give the 2 to the other side, we get 16. So velocity comes out to be 4 meters per second at that instant. So we actually bypassed figuring out the time. Another way to do it, a longer way, is to find the time and then from the time calculate the velocity. But we did it in just one shot. Okay, now we are ready to go ahead and calculate the normal acceleration. So normal acceleration, remember, is v squared over rho. We just determined velocity, that's 4 at that instant, and the radius of curvature is 2 meters, so it becomes 8 meters per second squared. So I'm going back to the last page. So you see at this instant, this is our tangential axis, and this is our normal axis toward the center of curvature. So now we already have the tangential component, we just determined the normal component, so kind of we have something like this. So this is the tangential component of 4, and we have a normal component which is twice as much, 8. So the magnitude of acceleration at that instant would be the resultant of these two components, something like this. And that would be square root of 4 squared plus 8 squared. And the magnitude of acceleration at that instance comes out to be 8.94 meters per second squared. So remember that acceleration, when an object travels along a curved path, has two components: a tangential component. This is the tangential component, which is just rate of change of speed, v dot, which was given. And then we have a centripetal component, an, which is calculated based on this equation, v squared over rho. Once you calculate those, then you can go ahead and find the magnitude of acceleration, which is a square root of, remember, magnitude of acceleration, as I just showed you, is tangential component squared plus normal component squared. You take the square root of that.